Now that we've talked about the graphs of our trig functions, we're going to talk about the inverses. One of the things that students confuse often is that the inverse and the reciprocal is the same, and that's not the same. So sine of x and cosecant of x were reciprocal functions. That's when we flipped it. The inverse functions, if you remember that from the beginning of the year, is when we switch that x and that y. We're switching the independent and dependent. So those two things are not the same. When we're talking about the inverse function, we are switching x and y. When we talk about the reciprocal, we're flipping that fraction. All right, so first we're going to start with the sine of x. And here we've graphed a small portion of the sine of x. I'm going to go ahead and sketch the graph just so you can remember what that looks like. It's the one that started at 0, 0, went up, and then it started doing this as it kept going. Looks something like that. There's our sine curve. What we've done is restrict our domain from here to here, because in order for it to be an inverse function, it needs to pass that horizontal line test. And so we start here and we go up to here, but then if we come back down, it would fail the horizontal line test right there. So we restricted our domain up to right there. As we move this way, we get to this point. Sorry, you can't see that. This point right here. And then if I went any further, it would fail the horizontal line test there. So we have restricted our domain from negative pi over 2 to pi over 2. And we do that so that its inverse is a function. So the domain is going to be restricted to negative pi over 2 to pi over 2. And then the range goes from negative 1 to 1. Now, for an inverse, we said we switch our x and y. And so if we switch our x and y, then we get this function right here. We've taken our x values and our y values, and we have switched them. For example, here we've got this point at pi over 6 and 1/2. And then if we came over here, we would be at 1/2 and pi over 6. That's where this point would be. So that's what we mean by switching our x and our y values. So this would be the graph of the arc sine of x, the inverse sine. So arc sine of x stands for the inverse sine. Now, earlier in the year, you also saw that written with the -1 up there. Those are interchangeable right there. They mean exactly the same thing. So sine inverse, arc sine are both the same exact thing. And so our domain would go from -1 to 1 and negative pi over 2 to pi over 2. Now, why do we do this? We do this because it helps us solve for the angle. So in most cases, we have found the ratios, the opposite over hypotenuse. Now, given that opposite over hypotenuse, I can solve for the angle. So we're going to ask ourselves, what angle from negative pi over 2 to pi over 2 has a sine or y value of that angle, whatever ratio we want here. Now, if you want to think about this right here, it doesn't look like it here because this is a normal coordinate grid, but if you think about the unit circle from negative pi over 2 to 2, so let's look at our unit circle. Here it is. It is a positive angle when it goes like this, and pi over 2 would be right here. It is a negative angle when we go this way. So negative pi over 2 would land right here. So we're talking about the first and fourth quadrant. That's where we're going to use our arc sines at. So this is quadrant 4, and this is quadrant 1. All right, so let's look at some examples of that. We've got sine inverse of 1/2. So we're asking ourselves what angle from negative pi over 2 to pi over 2 has a sine or y value of 1/2. That's what we're asking ourselves there. So you not only have to know the unit circle now, you got to kind of know it backwards. So sine, we're looking for which coordinate pair has a y value of that 1/2. And so if you remember, sine is positive in the first quadrant, negative in the second quadrant. So we know this is going to be in the first quadrant. And the one that has a y value is the coordinate pair that's √3/2, 1/2. There's that y value of 1/2. And that comes from pi/6 or 30 degrees. And so that means sine of 30 degrees is equal to 1/2. So you did a lot of this when we were talking about the unit circle. Sine of 30 and you would answer 1/2. And I would say sine of 60 and you would answer that. Now we're working backwards. We're saying the inverse sine of 1/2 equals what angle? So that's what we're looking for there is the angle. And so the angle would be pi/6 or 30 degrees. All right, so here's a second example, arc sine of negative √3/2. And so √3/2 comes from that point, 1/2, and then √3/2. This one is negative, so we know it's going to be one of the ones in the fourth quadrant. And I am going to use something that runs inside of this restricted domain. And so you can't always just look at it in the first quadrant and then make it negative. So the one that gives us a √3/2 as the y value there is that pi/3. And so we would say negative pi/3 or negative 60 degrees, because that's what falls in this restricted domain. It has to be from the first or fourth quadrant, and to get it in the fourth quadrant, you use the negative part of it. And so what that means again is the sine of negative pi/3 is equal to negative √3/2. So the inverse just allows you to switch those and solve for that different value. If you want to pause it and try, and then come back, you can do that. I will keep going with these. So the one that is arc sine, negative √2/2. Negative √2/2 again is in quadrant 4, and so we know we're going to need a negative angle. And the one that has the √2/2 is the ones with the 4 on the bottom, and so that is pi/4, or you can say negative 45 degrees. Arc sine of -1. That's this point right here. That's where our y value is -1. And so that's going to be at negative pi/2 or negative 90 degrees. All right. Now we're going to do the same thing with cosine of x, and then we'll do the same thing with tangent of x. So y equals cosine of x. If you remember the cosine graph, that is the one that starts at the top. And it looks like this. Again, we've had to restrict it in order for it to be a function. And so here we start right here, and we can keep going until we get to pi, and then it starts to go back up. So it would fail the horizontal line test if we continued. So this one we're going to restrict from 0 to pi. Still -1 to 1. And in order to find its inverse, we switch our domain and range, or our independent and dependent, our x and y, whatever you want to call it. We are switching that x and y. And so arc cosine would also be the cosine with the little -1 on top like this. That means that stands for inverse, so inverse cosine. And so we say what angle from 0 to pi has a cosine or x value of question mark. Now from 0 to pi on the unit circle, that is quadrants 1 and 2. So you don't have to think about that positive and negative angle there. It's all going to be positive since it's going from 0 to pi. So our first one here for our example, I'm going to say what angle from 0 to pi has a cosine or x value of √3/2. And so we know in order for it to be √3/2 as an x value, that's that coordinate on the unit circle. And the one that has that coordinate on the unit circle is pi/6 or 30 degrees. All right, so here it's saying the inverse cosine of -0.5. Remember, that's the same thing as -1/2. That's going to be in the second quadrant. And so we're looking for the coordinate pair that has -1/2 √3/2. The better you know this unit circle, the easier this is, and so we're looking for the one that has that x value right there, and that would be 2 pi over 3, or 120 degrees. Cosine inverse of -1, that's that point right there. We know that's pi, or 180 degrees. And then our -√2/2, we know that's the one with the 4 underneath. It is negative, so it's going to be the one in the second quadrant, which is 3 pi over 4, or 135 degrees. So make sure you know that unit circle so you can work backwards now to find those values. All right. Our last one here is tangent that we're going to talk about. The last inverse function is tangent. For our tangent one, if you remember what that looks like, that graph looked like this, and so it passes the horizontal line test as is. The only thing we have to restrict is that there's not one more than one cycle. So we've got one full period right here. That's what we have to restrict it to, because then it would fail the horizontal line test if we got the next one. But we do get a full period of the tangent one without restriction. So that's -pi/2 to pi/2, since that's where our asymptotes are for the tangent graph. Now the range is all real numbers, since it goes all the way down and all the way up for our tangent graph. Now, for the arctangent, that switches, so this would be our all real numbers to -pi/2 and pi/2. And again, that could be tangent inverse written with the little -1. So for this one, we're going to say what angle from -pi/2 to pi/2. And again, that's quadrant 4 and quadrant 1 that we want to look at in the unit circle, has a tangent, or in this case, y over x, because remember, tangent is your y over x of the given value. So this one's going to take a little more thought to get to it, because you're going to have to think about where this came from. So we've got the tangent inverse here of √3/3. And so we know this came from the y divided by x. Now, when it was √3/3, we know this has been rationalized. So we have to unrationalize that. And so we're going to multiply both of these times √3. And so that's going to give me a 3/3√3. And so those cancel, and we end up with 1/√3. Now, we said this top part came from a y and this bottom part came from x. So we know all of the values are over 2, which means that these canceled out. This had to be 1/2 and this had to be √3/2. But then when you keep change flip, those 2's cancel out. So we're looking for the ordered pair that is √3/2 and 1/2. Again, the tangent's the one that you're going to have to think most about, because you need to think about where it's coming from, y over x. And so it'd be this ordered pair. And so the ordered pair that's √3/2 and 1/2 is pi/6, or 30 degrees. All right, for our next one here, arctangent of 1. In order for it to be 1 when it's y divided by x, then we know they had to be the same exact values. And the only ordered pair that has the same exact value is the √2/2 and √2/2. And we know that is pi/4, or 45 degrees. For it to be tangent of 0, then we know this had to be 0 over a number, which is 1. That's the only possibility on the unit circle. And so the one that is the point 1, 0 comes from 0 degrees, or 0 radians. Now for arctangent of -1, that's going to be very similar to this one. The only difference is that one of these has to be negative. Since we're talking about quadrant 4 and quadrant 1, then we're looking at the one in quadrant 4. So it would just be this, but negative. So -pi/4, or -45 degrees, whichever one you prefer. All right. Those were the ones on the unit circle. You can use this as well with the calculator when we're looking for stuff that's outside of the unit circle. So I'm going to show you how to do that. You've seen the buttons already. On the sign here, we've got the inverse sign right above it, cosine is right above it, and tangent is right above tangent. So remember when we dealt with cosecant, secant, and cotangent, we did not use those buttons. We did 1 divided by sign because we flipped it. So there again, you see that difference. All right, so you will see that some of this in application problems as well. It says to find the angle, draw a picture and label. You will be missing the angle. So this is used to solve for the angle. We've done them where we're looking for the ratios. Now we're looking for those angles. Determine if it's sine, cosine, and tangent. Calculate in degree mode. Second, sine or cosine or tangent. And then the fraction mode if you want. This gives you the angle. So what is the angle of elevation of the sun when a pole 32 feet tall casts a shadow 14 feet long? So we've got a pole here, and it is casting a shadow 14 feet long. Our pole is 32. And so we're looking for the angle of elevation there. So across from this angle is 32 and adjacent to it is 14. So that's opposite over adjacent. So I would use tangent. So we say the angle is the tangent inverse. Since remember when we had the angle, we would say tangent angle equals and the ratio. Now we are looking for this angle. So we're using its inverse of 32 over 14. And so on the calculator here, we're going to make sure that we're in degree mode. And so that's the first thing I do. This is in degree mode. And so then I hit second tangent, and that's going to give me the inverse tangent of 32 divided by 14. And so we get the angle is equal to 66.4 degrees. So that's what you would be looking at in order to get the degrees. We're using that inverse. All right, we'll do one more of those. Stonebriar Mall is getting a new parking garage. The levels in the garage are 12.5 feet apart. A ramp from one level to the next level is 138 feet long. So I'm going to draw my picture here. The ramp is 138 feet, so that is right there. They are 12.5 feet apart. And so we're looking for that angle there. What angle does the ramp make with the horizon? And so we're going to do across from this angle, the opposite there, and then this is the hypotenuse. So we would need sine inverse of 12.5 over 138. And so to do this in the calculator, we hit second sine, and then 12.5 divided by 138. And so the angle is 5.2 degrees. So that's how you would do a application problem. I am going to look at some last ones here on the calculator just for you to see. This would be exactly the same thing. Our cosine, I would hit second cosine negative 0.7. And so there it is at 134.4. If I had it in radian mode, then it would be radians instead of degrees. So remember that. And so then you would do the same thing for this one, second sine, and second tangent. So that's putting it in the calculator. You will have to know both how to do it from a unit circle and how to do it on the calculator. Make sure you know that unit circle back and forth because we're using it for a lot of things now. To find those ratios, to find those angles, you've got to know the whole thing.